Now, we're going to start our discussion with amines by kind of painting a big picture of amines and then working into specific details. Now, a comment about what we're talking about with amines. We are not going to go really in depth into the naming of amines, and there's a practical reason for this. Amines typically are not the most reactive group, and so they sit low on the priority rules for naming organic compounds. The second is that when we focus on amines, this is kind of framing more peptides and amino acids, and this is going to kind of take a biochemistry biology approach. So when it comes to naming amines, we're going to stick more to simple amines, not like the big complicated structures we were doing like ketones, aldehydes, and things like that. Now, there's two aspects of amines we need to talk about. The first is their basicity. The second is just the nature of the amine itself. So let's talk about the nature of the amines themselves, and there's two ways we're going to focus on. The first is this idea of the degree of the amine. So we have primary amines, RNH2, secondary amines, R2NH, and tertiary amines, R3N. Now, in all cases, nitrogen here is going to have a lone pair. Now, we have to make this distinction though, because particularly with something like a tertiary amine, they're very large groups, and this nitrogen here really is not in a position to do something like nucleophilic attachment or substitution. Whereas in the case of the NH2 and the NHs, we'll see that because we can eliminate a hydrogen off the nitrogen, this makes this nitrogen much more available for forming bonds. Now, the lone pairs are going to be what does a lot of the chemistry for the amines. So the better a base these lone pairs are, the better they're going to be at doing something like nucleophilic attack or nucleophilic substitution. So how do we determine how good it is? Well, you probably already have an intuition that if we have really electron donating groups on these R groups, this is going to make the nitrogen better base. If they're more electron withdrawing groups, they're going to make weaker bases. But what I want to focus in this video is special subclasses, and these are aliphatic versus aromatic nitrogens. So an aliphatic nitrogen is one that is adjacent to an aromatic ring versus an aromatic nitrogen. And within the aromatic nitrogen, there's two cases. An aromatic nitrogen in which the lone pairs are not involved in the aromaticity, and aromatic nitrogens where the lone pairs are involved in the aromaticity. So the question is, which of these are good bases and which ones are not? Well, actually, our aliphatic are not going to be very good bases, and the reason they're not going to be very good bases is because of resonance. Basically, this is kind of what we see with oxygen near a benzene ring. These lone pairs can come down and participate in resonance structures, and because of this, they're not available as much for acting as a Lewis base, using those lone pairs to attack positively charged atoms or molecules. So actually our aliphatics here are not going to be great bases. Something like aniline is not a fantastic base. Now with our aromatics, there's a reason we have to make the distinction. If the lone pairs are participating in the aromatic system as they are with this compound, and determine if it is, go back and watch my videos on determining aromaticities. These will actually make these very bad bases in the sense that they're not very good at participating in like hydrogen abstraction. They can't accept a hydrogen. The reason being is that in order for that lone pair to form a bond to another atom, in order to act as a Lewis base, it has to break the aromaticity, and as you may have guessed, aromaticity is far more important than forming a bond to something else. But if we have something like pyridine here, where the lone pairs are not participating in the aromatic system, we have bonds that kind of are responsible for this. In this case, this is an exceptionally good base. And the reason it's a good base is that, one, the lone pairs are actually available for bonding, unlike in here where they're participating in the resonance and the aromaticity. The second is that being part of an aromatic ring means it's surrounded by electron density. This is a very electron-rich lone pair. And because of this, it's going to serve as a very good base. So with this framework, let's start talking now about how you name amines, or at least name simple amines.